And so thank you all for attending in this late day on Saturday in the final session. I'll begin by introducing all of our speakers with the bios they've provided to give us context for this nice panel on kind of hardware, software co-design to enable applications. And so with us, we have Ali Javadi. He's a research scientist and research staff member and manager of the Quantum Compiler Group at IBM. His research interests are in compiler and architecture issues in quantum computing, especially as they pertain to extracting the most performance from noisy hardware. He's one of the principal architects of the scaffolding programming language and the Qiskit quantum information package. He received his PhD in computer science from Princeton in 2017. We also have with us Professor Birgitta Whaley, who is the director of the Berkeley Quantum Information and Computation Center, professor of chemical physics at UC-Berkeley, and faculty science at Lawrence Berkeley National Lab. Her research focuses on quantum information, computation, mesoscopic and macroscopic quantum systems, quantum control, simulation, quantum dynamics, and quantum biology. Professor Whaley is a fellow of American Academy of Arts and Sciences, of the International Academy of Molecular Quantum Science, and the American Physical Society. We also have with us Professor Norman Yao, whose research lies at the interface between AMO physics, condensed matter, and quantum information science. A recurring theme in Norm's research is that much of the power of quantum mechanics is concealed if one focuses solely on systems in thermal equilibrium. Indeed, many directions ranging from quantum metrology to information processing rely upon production and manipulation of entanglement in systems that are far from equilibrium. Norman earned his undergraduate degree and PhD from Harvard, and following a Miller Fellowship, he joined the UC-Berkeley physics faculty in 2017, and earlier this year returned to Harvard as a professor in the physics department. We also have with us Kristan Temme, who is a research staff member and the manager of the Theory of Quantum Algorithms group at the IBM T.J. Watson Research Center. The research areas currently works in are quantum algorithms, noise, and complex quantum systems. He's received a diploma in physics from the University of Heidelberg in 2007 with thesis supervised by Thomas Gatzner, and completed a PhD in physics at the University of Vienna in 2011, supervised by Frank Verstrate. Between 2012 and 14, he was an Erwin Schrödinger postdoctoral fellow at MIT in the group of Edward Farhi, and between 2014 and September of 2015 was a postdoc in the group of John Preskill at the Caltech, and has since joined IBM Research in September of 2015. David Hayes, winning the award of shortest bio, got a PhD in Chris Monroe's trapped ion experimental group, and is now a senior manager for theory and architecture in the hardware division of Quantinuum. So thank you all for joining us. I'd like to kind of start out hearing a little bit from everyone on what they think about this idea of software-hardware co-design by leading with this sort of question, which is, we often lean on a digital abstraction in quantum computing to wash away some of the important differences between architectures. How do we balance the costs and benefits of abstraction versus kind of implementation details in physics and the actual hardware, especially in a co-design space? Said another way, how do we best learn from near-term experiments to a level deeper than the sometimes shallow response of, let's see how well it works, but with noise? And so let's maybe start out with, I'll just choose the order that I had written down of the participants with Ali.
Okay, thanks, Jarrod, and thank you for inviting me. So, yeah, I mean, I have been thinking about this question a lot in the past few years. To me, I mean, working with compilation and software, generally, I feel like software is cheap compared to hardware, and transformations in software are usually not that hard. I mean, well, there are difficulties, but so I guess what I'm advocating for is like the more you learn about the hardware, you can accommodate it in the software. So for example, yeah, like if you know something about, let's say, the crosstalk in your system, or if you know something about like the types of gates that you can implement in your system that are, you know, outside the standard library that you might be used to, then you know, you can formulate that as a problem and try to solve it and make the software take advantage of that. And you know, I think especially in the past 5 years or 10 years or something, that there's been a lot of that in different areas. Also, the other thing I think that I'm actually quite interested in is, going beyond this notion of, I have this particular hardware or I have this particular error correction code. How can I make use of these? Trying to come up with more sort of deeper trade-offs that then you can sort of customize to your hardware. So, for example, finding trade-offs between ancilla and depth of a circuit. So then, if you have a system where where qubits are cheap, then you can take advantage of that within that framework to reduce the depth. Or like this idea of, sampling overhead versus the depth of the computation or the errors that you accumulate, right? If you have a system that has a fast clock rate, then maybe you don't care about sampling overhead. And so I mean, these ideas that can be formulated outside of, these trade-offs that can be formulated outside of maybe a traditional co-design can then be employed within a co-design system so that you can sort of take advantage of it as you wish for the particular system that you have. So yeah, that's just my 2 cents.
Great. Yeah, maybe we could hear from Birgitta next.
Yeah, so thanks very much for the opportunity. I agree basically with the kind of things that Ali was saying. Primarily, my perspective is one of as a user. We develop an algorithm and we want to then implement it. So we look around to see what is the most, the best hardware right now. But I think it's very, very important that we know the noise and that we can then think about ways to mitigate the noise in software, so including control techniques or randomized compiling and so on, depending on the kind of noise. So that's really important. I think that in any machine, the noise is actually characterized today, and also as it changes, as the hardware updates continue, that that there's continual updates for the noise and so on. But also, so Ali mentioned trade-offs with ancillas. So there's another trade-off with ancillas that one can make, which is ancillas versus noise. So we recently found that if you add some ancillas to a quantum machine learning network, tensor network model of quantum machine learning, that by adding ancillas, one can actually mitigate to some extent against dephasing noise. And if you add the ability to do control on the coupling between the ancillas and the logical qubits, then you have another whole set of handles to explore in terms of developing further. So I think that's a good point, that if your ancillas are cheap, then maybe think about what else you can do with them other than just doing measurement and readout. Yeah, that's
great.
My key point.
Thank you. And how about you, Norm?
Great. Thanks so much for the opportunity to give some thoughts. I think maybe I'll start by saying that I think both things are necessary. I do think that this idea of co-design between software and hardware is extremely powerful and very important. And I think Ali and Birgitta mentioned some very good points. I do think that, at a very high level, the abstraction does give one the power to ask the question of what are the types of problems that one can solve without necessarily, worrying too much about what is available in terms of the types of gate sets and what is, scary in terms of the types of noise that needs to be mitigated ultimately. So I think that there's certainly some space where having that abstraction and thinking deeply is important. But to the point of kind of co-design, I would kind of maybe make 3 points. I think you're exactly right, Jarrod. I think, many of the things that, for running algorithms on different platforms, many of the things that, the platforms ask, the first thing that they ask a theorist or someone who proposes a platform, a circuit is, okay, what happens if you add a depolarization channel or some very, very simple noise source at a few % level? How does this change your observable? And of course, if you say, well, this totally messes things up, it's maybe a scary prospect. But I think that at a broader level, it's getting to the point where I think that there's a question of what exactly can one learn about the noise and how can one learn it? So I think that, at small scale systems, of course, comparing to what you expect for the exact answer and trying to extrapolate makes a lot of sense. But I do think that we are starting to be in a regime where it would be really interesting to see kind of a concerted effort to benchmark across platforms. I think there are now multiple platforms that claim to be able to sort of go toward the, beyond 50 qubit limit. And I do think that at that point, it becomes very, very, difficult to do classical simulations of things like dynamics in the first place. So having some concerted effort across different platforms and different teams to verify and understand the noise across these platforms, I think would be very powerful. And that is one way where I think you would be able to maybe learn something more than just say, let's simulate with a master equation some type of noise channel and see whether it agrees with the data. I guess the second thing I would say is that at the level of noise, I do think that many of the systems at the moment maybe don't require super detailed and subtle noise models, but I think that long-term, a vision towards really trying to deeply understand correlated noise. So noise that ultimately in a device, as Ali was talking about with respect to crosstalk, you expect there to be correlations in the noise, whether it's correlations in time or correlations in space. And we know that in principle, if you do have correlated noise, one can do better. One can note these correlations in the software and ultimately be able to mitigate that in a much better way than one could with purely white noise at some level. So again, I'm not sure whether or not we're there in terms of needing to, that being the bottleneck, but I do think that long-term, this vision of sort of thinking carefully about software and hardware co-design at the level of mitigating noise that's especially correlated would be very, very powerful.
Great, thanks a lot, Norm. Kristan, love to hear your thoughts.
Hi, Jarrod. Thanks a lot for running this and let me give my 2 cents as well. So as to your question, I think what would be actually the desired level, what kind of access would be important. I think that is sort of also a question of time in terms of how fast or how far things progress, right? I think on the ultimate level, what you would want is something that is just highly abstract and you can basically easily implement your idea. But currently we are in a stage, which is this very, very much this co-design stage, where you really do need access to the device on a very low level. So case in point, I mean, earlier last year, we were running some error mitigation experiments. And what happens is basically that they're sort of very, very closely tied to the hardware, to which gate you run, where you run it, and so forth. And suppose if you were to go into abstract away a lot of things there, then nothing that we've learned about the noise that we tried to mitigate would actually apply anymore, right? So I think at the current stage, to have the ability to do proper co-design, yes, you need very close to hardware level access, maybe not too close. So I personally don't care on how people do qubit readout specifically. I just want to know it's possible to do that, and there's some error model that describes it in some extent, but sort of close to the extent there that I know that, okay, if I definitely implement this, this is what actually physically happens on the device on a theoretical level. And I think the goal should be ultimately to sort of to come up with a software stack that grows in the sense that once you basically have these pieces and parts, you wonder how much of that is automatable and how much you can basically abstract to the higher level, I think. So I think to me, like which level you want is probably going to hopefully evolve to the extent that you come to a point where you go really abstract high level and can use these things, and a lot of stuff runs underneath it. And currently you just need something that you can try out that actually works. And for that, you need closer access to the devices, I think.
Great, thanks, Kristan. Yeah, I'd love to hear, Dave, your thoughts.
Yeah, I think I might be maybe closest to Norm on this one. I kind of think both is probably ideal. So I mean, and when I say both, I think, you know, learning the hardware, I kind of feel like that's really important for people that are working on the stack and people that are developing the tools to accept quantum circuits from people like algorithm developers. So, you know, I think people working on the stack, they kind of have to roll up their sleeves and learn all the different weaknesses and strengths and program accordingly. But I kind of think algorithm developers are a little bit of a different beast. It's great if they want to get in and learn all the dirty details about all these machines. We should encourage it and help them out. And I think careful measurements and reporting can go a long way. But I do think there's probably a limit to what we should expect them to do, especially with all the different platforms out there. And, they have their hands full too. They're doing really hard research just developing these algorithms. And so I think, to sort of make it easier on them, I would advocate for developing tools to sort of automate some of the work. And I think there is some work being done along those lines. I think it's too bad Microsoft isn't here, or somebody from Microsoft, to talk about the QIR, this quantum intermediate representation. I think that's a really promising avenue. And for those of you who don't know what it is, it's a tool that interfaces with all sorts of high-level programming languages on one side and interfaces with all sorts of hardware on the other side, and can optimize the programming instructions for different hardware. And I've personally seen really impressive results from this. I think the best example is Q# for me, which I think, for those of you who don't know what Q# is, it's a programming language developed by Microsoft, and it's incredibly abstract. There's not a lot of getting under the hood with this thing. It almost looks like Mathematica. You type in like quantum Fourier transform or something, and list the qubits, and it does it. I think that's where everybody wants to get to. But the first time we tried to use it, the results were really bad. And when you got under the hood, and we can do that because we can look at what the machine's actually doing. There were qubits kind of sitting around waiting and dephasing and doing things they shouldn't be doing, basically. Anyways, this QIR, it just fixes all that. And so, they haven't really reported on the results yet, but I think people will be pretty impressed when they do. So I'm hopeful that we can build tools to let algorithm developers be algorithm developers, and let stack developers be stack developers, I guess is my position.
Great. Any other general thoughts on this topic before we move on to another question? All right, sounds like people are somewhat satisfied with Q# and whatnot. To kind of pivot a bit. So discussions of quantum advantage over classical techniques often focus on sort of easily defined computational problems. And by that, I mean, you have some classical inputs and some classical outputs. There's often a right and wrong answer. Are there tools that could be developed that would help us explore where quantum computers can be useful in a slightly different way? What I mean by that is many of you work close to hardware or have in the past, or a theorist and computation people that think about these things across different architectures, where, say, if you fail to build a quantum computer, arguably you've built a great quantum sensor, and vice versa. Is there some sense in which we can kind of play with this duality, use its ability to be a quantum sensor across multiple qubits, and then maybe switch it into a mode of operation where we can really start to think about, say, processing directly on data? And I guess I would consider this co-design in a way, because it's pieces that we already plan to have in the lab. And so, yeah, how do we think about building tools for this space, understanding the problems we can address, get close to the physics, but also close to things we're learning about the world in a computational sense? And so maybe I'll switch up the order this time and go in reverse, unless we'd like to freeform, but maybe I could start with Dave in that case.
Yeah, sure, thanks. They sent us these questions ahead of time. So I'm not a sensor guy, so I did a little reading last night. And in particular, I looked at Professor Caballero's work. She talked a little bit about it today. And I skimmed this paper where she was investigating, using quantum error correction in quantum sensing, and I thought that was because at first I didn't really see a way to marry these two technologies because they kind of have really different requirements, and it's pretty tough eking out these requirements anyways. But anyways, that paper was really interesting to me, and I, she already kind of went over it, so I don't have to go over it again. But like one thing I was thinking was that, well, if quantum sensing really was going into the regime where they're using big entangled states and doing error correction to improve results and whatnot, proving that stuff out on a quantum computer is a really good platform for testing these things. And they do a lot of nice analysis in that paper to show that how these systematic shifts show up and things like that. But they have to make a bunch of assumptions and stuff, and there's nothing like testing these things out in the real world and fine-tuning them. So I think it would be really cool to explore how real world noise affects these quantum error corrected sensors, and what sort of codes would work best for different noise environments and correlated noise and all the dirty real world realities that would come in a quantum sensing environment. So it's something I haven't explored very much, but I would encourage the sensing community to reach out to people building these quantum computers and see what sort of questions we could explore together, because we talk the same language. We're just not really working on the same problems in the lab. I mean, it's all quantum physics, of course, but we have very different goals and stuff. But that doesn't mean we can't solve some of these things together. But anyways, not a lot of specifics on my part on this one, but.
Great, thanks. Kristan, what do you think?
Cool, thanks. So I actually think that's actually a pretty interesting question, especially coming from the computational side. The ask is, so is there something that basically goes beyond using your qubits as awesome magnetometers, which they are very well at, we're doing a very good job at. And the wonder is, so is there some point where you could actually use the quantum computation that would help you in some sensing task? And what I was thinking is a bit, so there are some tasks like when you're sitting somewhere in hypothesis testing, right? So you look at sort of a hypothesis testing scenario where you basically say, someone gives you either state rho or some state sigma, and now you get like n tensor copies of those states, right? And when you get these n tensor copies of either rho or either sigma, then and you try to sort of say, okay, you're happy with the scenario that your type 1 and type 2 error, they're exactly the same. And then what happens in that setting is basically, actually what the optimal measurement would be that you would like to do, because it would be essentially a Hollywood-Hellstrom measurement, right? And so, so you project basically on the positive definite part of their difference. But I don't think there's technically any realistic handle on how you explicitly construct that particular measurement, right? So in theory, it has to be projected onto that positive semi-definite part, but yeah, I don't know how you would ever do that in a circuit or how you'd implement that in a circuit and so forth. And it's sort of interesting because you could rewrite this entire problem as an SDP, right? And we have algorithms, quantum algorithms for solving SDPs on large spaces, and they're nice with few constraints and whatever. So I think it would be interesting to go in that direction, explore these types of optimization tasks to essentially see whether there is some way, if someone sends you a bunch of copies of those states, that you could run a quantum algorithm to actually construct close to the optimal measurement by solving an optimization problem, SDP type optimization problem, a la Svorey and Brandau, right? And I think it would be actually a pretty interesting setting, because the problem with that algorithm is that the error dependence in that algorithm is, so most classical SDP solvers, they have like logarithmic dependence in the error that you want to produce. And so all these multiplicative weights things, they get sort of a polynomial type error in so it's not logarithmic, it's polynomial in that error. And that might be a setting where this actually works, where this is sort of acceptable as a constraint. So I think that in general is an interesting question or ask one could pursue. And I'm sure there are more questions like that. I think it's difficult though. I mean, that's probably an interesting academic pursuit. I think it's very difficult to come to a point in the very near future where you nicely couple these things, right? So you must have, I don't know, some sensor that brings stuff into a quantum computer, and that's probably work to get that to work, essentially. And I mean, it looks like an interesting problem, yeah.
Great, thanks, Kristan. Norm, do you have some thoughts?
Yeah, actually, I also really like this question. I'll split it into two parts, but I'll try to be very precise, in the two parts about at least how I'm thinking about it. So the first question is maybe just a question about kind of the nature of quantum advantage. And I do think there is a tremendous benefit to being precise. So the fact that one does try, and I think many of the quote unquote quantum advantage experiments are sort of in the space of being very distinctly mappable to, or trying to be very distinctly mappable to known hard problems, I think is very powerful. Because in the end, you want to be able to make a sharp statement or a very precise statement that sort of is not something that's sort of based on generic expectation. At the same time, I think my perspective is maybe that there's a little bit of worth to being a bit more broad when one thinks about quantum advantage. And maybe let me offer sort of everyone to think about this question for a second. So one might say, for example, that a quantum advantage statement is that you'd like to solve a problem, or you'd like to answer a question, and you'd like to demonstrate that the answer to that question with some quantum input is something that you can do, but that without that quantum input is something that you can't do. And so I've had discussions with some of my friends about this. You might say that every measurement done on a quantum material is that. There's very, very complicated Hamiltonians that describe strongly interacting electrons in these quantum materials. And I wouldn't know if I posed you a question and said, calculate for me the thermal Hall conductance or some other property of this strongly interacting Hamiltonian, we'd be hard pressed to do it. But it's very hard to formulate that question into a precise computer science, a computational question that is, reducible to an NP hard problem, or just reducible to anything. What exactly is, calculate a thermal Hall conductance? But people measure thermal Hall conductances using quantum materials. And you might say, okay, well, that's like really messed up because, now the quantum material is like it's some rock, you can't say that's doing any computation. But let me abstract a little bit more and say, okay, you take the same Hamiltonian and now I give you a quantum simulator. It's not a full-blown quantum computer, so it can't, do anything, but it can simulate a very specific subset of classes of Hamiltonians. And let's say that within that subset of classes of Hamiltonians, you still don't know how to calculate a thermal Hall conductance, but your quantum device can measure a thermal Hall conductance because it can simulate an example of this Hamiltonian within this very specific class. Is that quantum advantage or not? Presumably within the sharp definition of I'd like to reduce this to a classically intractable problem. No, it's not, because I don't know how to reduce the calculation of a thermal Hall conductance to that. But pragmatically, in terms of thinking, about whether or not you are doing something using a very controlled quantum object to answer a question that would be hard on a many-body Hamiltonian otherwise, that might give you a different feeling. I don't know what the answer to the question is, but at least that's something that I think is an interesting dichotomy to think about. So that's, sorry, I'm going to wax a little bit poetic. So that's the sort of some of my thoughts on the quantum advantage side. The second question, I think, Jarrod, is also it's a remarkably deep question, but I think one really has to think for us 1 second about where exactly does one win, if at all. So I would say certainly at following up on sort of what Dave and Kristan said, at the level of just the statement that entangled states can do better sensing, certainly true. But I think the question maybe that's posed is a little bit more specific. It says, imagine that you have some object, a quantum object, and you have classical inputs and then outputs. If I now have quantum inputs, can we do better? Where do we win? I don't know that we win super broadly across all domains, all across all problem spaces. But there is one place where you win. And that is in trying to, I don't remember who emphasized the readout or mentioned readout as a word. There's one place where you, I think, probably win from this sort of quantum input perspective, which is in reading out information from an entangled object. And so here I sort of come from a little bit of a quantum sensing background. In general, quantum enhanced sensing just says you have some entangled object and you'd like to make measurements on a field that it gives you better sensitivity because of the entanglement that you have within the qubits, as opposed to just classical correlations. But to read out that information is very hard, actually. So you ask yourself, there's kind of like maybe 3 levels of distinctions. So if your system is sort of, if you cannot measure individual qubits in your system, then the gold standard at some level is to get to the quantum projection noise. If you're limited by noise that, where you don't even get to the quantum projection noise, then it's very hard to change properties of your system to make improvements on the measurement. Beyond the quantum projection noise, you could ask for single particle resolution. So maybe you want to do entangled sensing with many, many qubits. And if you can measure each of those, read them out individually, you are better than quantum projection limited. And maybe you can even do a little bit more. But still, it doesn't allow you to read out in a very easy way information that you get from accumulating phase on an entangled state. The sort of most general way to actually back out information, in some sense, is basically to uninvolve that entanglement in some way. And there, I think, is one very specific and sort of nuanced example where a quantum input immediately wins. So the rules of the game are the following. I give you a quantum entangled state, and I tell you that the state can do better measurements. You take the state, you go send something. That phase or whatever the information is encoded in that new state, that time evolution of that new state, and you ask, how do you read it out? Okay. And I would say that the most general way to read it out is to make a circuit that undoes the entanglement in the first place. If you time evolve to get that entanglement, it's backwards time evolution. And in that sense, actually, I think that would be a place where the quantum input and then some algorithm on top of that would be ultimately more powerful than the usual way we do readout, which is sort of, either quantum projection noise limited or single site resolution limited. It'd be a much more powerful way to read out information from entangled states. So I actually don't know that there are a huge ton of examples like this that are obvious to me, but that's one context where I do think that the quantum input immediately automatically wins over the classical input.
Great. Thanks for the detailed example as well. Birgitta, your thoughts?
Yeah, so I don't think I have very much to say about sensing. I haven't really thought about that too much in the context of quantum advantage. But I think it's true that the notion of quantum advantage should be generalized from what's currently perceived. As you said, it's usually described in the context of very precise statements about explicit problems that are known to be hard, and it's typically something like statement like for instance in quantum chemistry, the statement is for the true ground state that but then one has to take, I think one has to generalize it a little bit more to take into account what people in these disciplines actually do, because you don't actually normally, for instance in chemistry, look for exactly the true ground state. So that's kind of like looking for quantum advantage there is it's kind of interesting, but it's not really relevant to what people do in the field. And people in chemistry, for instance, are usually looking for things within a certain tolerance called chemical accuracy. And that's a different kind of beast then. And I think also similarly, and also there's a great effort to reduce the scale of polynomial scalings of classical algorithms. And that's something also in quantum machine learning, where, there's been in the last few years, these great advances in classical machine learning, and Yuan Tang's results showing that you can have polynomial machine learning, but if your polynomial is order 26, that's a huge difference than if your polynomials of order 4 or 5. So, and I would say that in practical terms, at least today, that would be a quantum advantage. If you can get down from 26 from a classical algorithm to 5 or 4 today. And similarly in quantum chemistry, there's things you can do which are intractable on any machine you can imagine in the next 20, 30 years. But you could do them, if you can do them, by reducing your polynomial scaling significantly, then that's an advantage. So I'm afraid that's nothing to do with hardware co-design or anything. But I think it's the right time to rethink in general what notion of quantum advantage, not only what notion we have, but how we want to define it for specific different domains. And so applying it to sensing is a great idea. I don't have too much to say about that right now.
Great, thank you. And Ali, your thoughts?
Yeah, I'm not going to pretend that I'm an expert in quantum sensors, but I guess I interpret the question as problems with quantum input and quantum output. And so, I mean, yeah, I don't know much about applications, but I spend most of my time thinking about compiling. So here's one possible problem that could be formulated along these lines, which is, so like the idea of state preparation and finding a circuit or the most efficient circuit that prepares a state. You can, there are classical methods. Given a classical description of a state, you can find some circuit that prepares that. But then there are also these ideas of quantum-assisted quantum compiling, where like you basically formulate the problem as an optimization problem that you can then use some quantum algorithm for optimization to solve it. And so maybe that's one use case for this, where like the input is as you load a quantum state to your quantum computer, where then you don't, there's no efficiency problem, so you can efficiently load a large state, and then use the quantum computer itself to find some parameters that will later on become the answer, which is like the circuit that prepares that state originally. I have no idea if this is a useful problem or anything like that, but I thought I'd point out maybe some connection to compiling. I don't know.
Great. Yeah, thanks everyone. I wanted to mention to the audience that if you'd like to ask a question for the panel, you're welcome to do so in the chat, and I'm happy to incorporate that. Now we've had a good chance for everyone to talk. Maybe I'll throw in a slightly spicier question and allow people to just sort of free-form respond rather than go through everyone. But if we like, we can still cycle through. And I guess that question is, so this sort of session is nominally about, enabling applications with hardware, software co-design. But I would say a number of industrial and other efforts have taken the point of view of sort of, I guess I would say, thresholded co-design, in the sense that the promise of an application on a near-term device does not look substantial enough to alter the engineering pathway for that company. And basically they will bet on something like quantum error correction or a large-scale quantum device and make all of their engineering decisions sort of solely based on that roadmap, unless overwhelmingly convinced otherwise. And so from that point of view, they're saying maybe that co-design in the near term is not as relevant as we might want apart from creation of the error correction code. How do we feel about that characterization, and whether that's a good move if it's true at all?
I can maybe offer some thoughts. Yeah, I think I know where that's coming from. It seemed like the word co-design came from the classical computing field, where they were co-designing hardware with algorithms, and they were both kind of moving forward. But our field's different. The algorithms are over here and the hardware is over here, right? And so in some sense, we're trying to push the hardware forward and sort of bring the algorithms backward. That's probably the wrong word. We're not bringing them backward, but trying to do more with less, And so in our case, it doesn't really make a lot of sense to go all in on one algorithm at this point, because the machine's going to have to be so huge and different than what it is now. We have no idea what kind of problems we're going to come up with when we try to put that thing together. You know, who knows what the story is how it's going to unfold. There's some co-design happening though with like lower level, I guess, subroutines or something like that you would maybe call them. Like, I would say we're co-design, you know, we're not co-designing with high level algorithms, but we're co-designing with error mitigation and general quantum error correction primitives, if that makes sense. Like trying to optimize the feedback on syndrome extraction circuits, and just put in the hardware that we think is going to be, you know, most broadly applicable to open up as many avenues as possible, and then push forward. And, you know, hopefully as the hardware gets further and further, and then we can kind of start honing in on what error correction codes might hold the most promise, and then maybe start to fork. But, you know, right now we're trying to keep as many doors open as possible, because it's just too early, I think, in our case.
Maybe I can say a couple of words about the IBM side of the story. So the reason in my first answer, I emphasize that, you know, software is cheap, is that it really, like, if you can do something from the software side, having learned something about the hardware, noise, or things like this, then, you know, you should probably just go ahead and do it. It's not hard. On the flip side, you know, changing hardware takes time, takes money. But I would actually say, I mean, there are examples of this. So, like, for example, I think an excellent example of co-design is this heavy hex architecture of within IBM, which is basically, you know, in fixed frequency superconducting devices, we have the problem of frequency crowding and crosstalk, and so we cannot make arbitrary connections. On the other hand, you know, we want to run error correction. So essentially, the hardware and the code were kind of designed together to support that. So that's just kind of a strike balance between a code that has not too bad of a threshold, but also a device that we can design and scale up to, you know, hundreds of qubits. And so that's basically been the road that IBM has taken. That's just one example. I mean, I would say there are other examples. So, for example, like, if it turns out that, you know, calibrating a new gate helps some application, you know, that's again something that, you know, experimentalists will do. That's not really changing hardware though. It's calibration, it's software calibration. But yeah, I mean, I would say if there's an overwhelming example of, you know, a specialized hardware making a huge gain in some area, I think people are open to designing that kind of thing. But yeah, I mean, the bar to meet that, to change hardware, is much higher than the bar for software. I mean, changing software is not hard. So.
Yeah, maybe I'll riff on what you said, where you said, certainly there's been efforts in co-design with respect to error correction. And so if we push that a little bit further and we consider error correction the application itself, let's imagine a not too distant future where everyone here has been wildly successful in building their devices. They've co-designed for error correction. We have 1,000, we have 10,000 physical qubits. We're doing experiments that push the limits of known physics with kind of stabilizing exotic quantum states with only local measurement and feedback. And yet we step back and then we take a logical qubit or computational point of view, and maybe we find that we have between 10 and 20 logical qubits that we can do a few gates on. So how do we flip the script and really make error correction the application? Maybe this is closer to a physics question of these exotic, interesting quantum states. How do we use these as our application to understand the limits of our physical world? Is this possible, or is this only a milestone on the way to computation?
maybe I can quickly, I'll offer a few thoughts there. I think the question was so elegantly phrased that it kind of answers itself, which is a good problem to have. But I think one could almost end it by saying yes. But I was going to say something along the virtues of co-design. So I think that, I don't know as much as Dave or Ali on this topic, but I do think that, it's not something I've thought about, Jarrod, but the statement that you're making that, yeah, okay, it's like we talk about co-design, but at some level, nothing is so shiny that, we're veering away from this goal of getting to large scale error correction, right? I think and I think that if I were coming at it from a computational perspective, I think that's probably, I would generally agree with that. But I think what you're asking us to think about a little bit is to zoom out and say, like, okay, there's many places, or subfields where, quantum devices can make inroads. We've talked about quantum sensing already. We've talked about computing for sure. And now you're asking us to think about quantum simulation. And I think that at some level, I do think that this notion of co-design is very much an aspect of almost all of the best quantum simulators. As an example, I think of the type of co-design that I certainly think about a lot. The first thing that you often think about when you're thinking about simulating something about a Hamiltonian is whether or not the question you're asking is a dynamics question or a ground state question. So the Hamiltonian is the generator of dynamics, but its extremal eigenstates can also exhibit order. And the question is, are you asking for a quantum simulation of one or the other? And there's immediately you do co-design, because if you want ground states, then you need to ask yourself, how exactly, is there an algorithmic approach or a hardware-based choice that allows me to actually access those ground states? So how do I cool down the system? That's oftentimes one of the toughest things to really do in these isolated quantum simulators. And there, if you can't have a direct route to cool, oftentimes what you go for is really time-dependent controls. And again, at the level of software and level thinking about algorithms, there's lots of beautiful work. Birgitta, for example, has done some very elegant work here on the importance of time-dependent routes, for example, to try to adiabatically prepare low energy states of a complicated Hamiltonian. On the other hand, if you're interested in dynamics questions, you also, I think you take a very different path, because dynamics questions, you'd like to know how things move. And for how things move, I'm not so worried about really precise global time-dependent controls. I'd like not so precise, but very local controls so that I can actually figure out where information is moving relative to a particular location. So I do think that, at the level of quantum simulation, the notion of co-design is much more natural in some deep way. And I think that in that sense, if one can be satisfied with the idea that one is asking very hard physics questions, I think going back to the idea that Birgitta and I mentioned, what exactly, what is the advantage you want to win? If you can really measure something that is extremely hard to compute in a strongly interacting system, is that advantage enough for us? I do think that with that perspective, you kind of immediately veer onto the path of co-design in a very natural way.
Great. Other thoughts on this topic?
I guess also from a planning perspective to your original way of how you phrased the question, basically, right? I very much agree with what Dave and what Ali said, is that you don't throw over hardware plans that you have on a whim because you have just, that might be interesting, or that might be interesting, or that might be interesting, because you'd be producing a ton of different devices on evidence where you say, well, it feels right? So, and many other things. However, then one could take the other extreme of saying, well, we're going to sit down and say, the only thing I really know and understand really well at this current stage is the surface code. And now we're going to go, and that's the only thing we'll ever build. And we try to build better and better devices until we hit the surface code, right? And so forth. And I think when one does that, one misses out on a few things, right? So one thing that it might be missing out if one were to do that is, I don't know whether at this stage we already have an idea what the final code should look like, right? So it's that might be very, very, very challenging, right? So I don't know. I mean, the surface code is cool because we've studied it to death, right? But I don't know whether that's already the best there is. And I guess if you look at recent results, there's really hope for improvements in terms of nicer LPC codes and so forth. So it's very difficult to plan that far ahead in essence and try to devise something. Then the other hand is, sure, you can, I think the crux has to be that you start building progressively larger devices and play with them and see what breaks, what works, and do build stuff that way, right? That's one thing. The other thing I think is, I honestly believe that having a fault-tolerant quantum computer is still quite a bit off, right? And in the meantime, you have devices that are actually interesting, right? So they may not do exactly what they want them to do because they're very noisy and they're very annoying. And it would be a shame not to seriously explore what you can actually do with those devices. So if one were to sit down and say, well, let's drop this, say, co-design the idea, and basically say, we have a very clear focused path, we want to go there, and ignore everything left and right, then there might be the chance that you might actually miss out on things that are interesting, right? And so forth, because it's really, so if you don't try, I mean, you won't know, right? So when it seriously has to try on that end, I think. And so that's sort of the perspective on whether you believe this stuff to be sort of a step function, where say, okay, now we burn so many hours of labor and resources in the hope that sort of in 20 years down the line, there's going to be the shiny fault-tolerant quantum computer where we know we can run algorithms that have provably exponential speedups, as opposed to, sure, in the meantime, it would be worthwhile to also dedicate some resources in trying to figure out whether you could do something else with those devices, right? And so yeah, so I think that's roughly my perspective on that. Right?
I just want to endorse Kristan's opinion. So well put. I was thinking all the same stuff. Yeah, I'm like waiting with bated breath on more results on these LDPC codes. I mean, we could go all in on the surface code now, but I just don't want to lock us in on something like that when there's possibly much brighter futures. I kind of like try to remind myself of like, okay, if I was in the 1950s or something and I was gonna lock in on how to scale a classical computer, like I would have made some really dumb decisions. I would have probably said like, okay, we need like a huge pile of punch cards and we're going to be feeding them in faster than you could ever see, you know, and it's just not the way it happened, right? And anyways, I try to remember stuff like that. Like I try to keep an open mind, and I don't want to lock us in. We got a long road ahead of us, is all I'm saying.
I can add a comment on that too. I mean, so generally one thinks of, as a theorist, one thinks of co-design. Okay, so we work with the experimentalists and there's some backwards and forwards and so on, but it's more that that we tell the experimentalists, oh here, so like for instance, LPTC codes, they look pretty good, so maybe that's interesting for you guys to explore. But I think the other direction's also useful. You know, given the limitations that you currently have, it is actually worth spending some effort as theorists to look at this. I mean, otherwise, for instance, the whole field of flag qubits, that really arose because of limitations with complete fault tolerance. So then, you know, Ben Reichert thought about, well, what about just a little bit of, going a little way on the road to full fault tolerance? And those are, you know, that's a very interesting and a very productive direction right now as well. So I think, you know, so I think for theorists also to think about, well, so what are these, so how can we get around these constraints? There will be new things coming out. And I think that's actually a valuable exercise right now as we're waiting for full fault tolerance.
Great. Yeah, thanks for the spirited discussion, everyone. You know, maybe I'll leave with the final thought of circling once that analogy that Dave and maybe Kristan had made there. for computing is that there was a one transistor application that was monetizable, as we all know, kind of things like the hearing aid or maybe a few transistors in the op amp. And that certainly made the risk profile of developing one such computer, even if you didn't know anything, much lower. So returning to applications, one might ponder after we leave here today what the one logical qubit application is that's going to carry us all the way to fault tolerance. But we are running out of time. I apologize, I did not get to the questions that were asked in the chat. Maybe we can afterwards, but if you'll all spare me 30 more seconds per person, if anyone, we can run through, and if any of us have closing thoughts to close out this session, and I think pretty much the entire workshop. I'll run back through maybe in the original order that we did. So sorry to surprise you with this, Ali, but yeah, if you have some closing thoughts.
No, thank you, Jarrod. It was a pleasure being on this panel. I would just say, yeah, I think I agree a lot with what Dave said at the end, which is to sort of keep an open eye and an open mind and think, kind of evaluate new ideas, because some of these ideas might really be paradigm changing and append a lot of the things that we've kind of taken for granted in terms of the stack of computing. And which is why I'm a little bit skeptical when I hear about these resource estimates and things like this, which I mean are nice exercises to do, but changing one thing in 2 years might completely change the picture and change the way we go about solving some of these problems in terms of encoding, in terms of compilation, et cetera. So yeah, I think the road is kind of wide open, and we're going to see a lot of surprises, I think, going forward.
Great, thanks. Birgitta, closing thoughts?
Yeah, I think that notion of the reminder to update things as you go along, I think that's actually very useful. So resource estimates for algorithms should be updated definitely as one goes along. In fact, there's a number that one can cite, and a whole number of things that have been out of date, updated over the last 8 years or so. I think in general, I would say again, we have to generalize our the way in which we characterize, or the way in which we want to think about quantum advantage. That actually would help the field, I think, as a whole. And then Jarrod mentioned what can you do with one qubit? I don't have an explicit idea right now, but I suspect there will probably be a sensing application for that. One hot qubit which would be connected to possibly other noisy qubits or a quantum simulator or something, but something which is driven by the ability of one qubit. I think that's an interesting thing to think about.
Great, thank you. Norm? Yep.
Yeah, this has been a lot of fun. I guess along the lines of sort of what both you and Birgitta were saying, I do think that, in terms of maybe a few qubit application, I'll say two things maybe. One, I do agree with everyone, and I think it's kind of a very special time where we are getting to the point where, maybe we're not at error correction, but we are getting to the point where there are enough physical qubits in the system that makes, it not super easy to simulate directly on a classical computer. And that is a milestone in and of itself. And there's multiple platforms that are sort of pushing towards that milestone. So I think the timing right now is quite special in that sense. And I would say, with that sentiment being expressed, that perhaps at this stage, application is not few qubit, but I do think sort of scientific discovery and just understanding and being able to ask questions that we won't be able to calculate either directly analytically using perturbation theory or computationally using DMRG or exact diagonalization. I think that is a very, very compelling reason to sort of push forward on this path. And I think the more acceptance that the community can foster for that perspective, the better we'll all fare in the long run.
Great. Kristan?
Yeah, I don't know whether I can add anything thoughtful at that point. I agree. No, I think that makes a lot of sense. And I actually like that point. Yes, we are looking at devices that are pretty big. And they're noisy still, but there's still things you can try. Right. So I don't know. I don't think I have anything thoughtful.
Great. And Dave, would you like to close out our panel?
Sure. This is a lot of pressure. So I guess I was going to close with sort of a call to arms for the NSF. I kind of see the NSF as a good tool to bridge the divide between academia and industry. So I mean, I don't want to get into it, but there's some divisions there, and a lot of the best hardware is in industry, but a lot of the best research is going on in academia, and it'd be a shame if we weren't working together. And I think I'd encourage the NSF to look for ways to bring the students and the professors, sort of pool resources and give them access to the industrial resources that are out there.
Awesome, thank you. A beautiful final call to action. And I'd like to thank all the panelists. And then maybe before everyone runs off, I'll call on our fearless leader, Yufei, to see if there are any final remarks or other thoughts.
I really like the discussion, like we're very thoughtful, and I hope I can join, but great. I think that's all for today, and also that's all for the workshop, and maybe later we will have a write-up, so I may bother you. Okay, thank you.